Up to this point, I've been guiding you quite a bit on the kinds of neural networks that we've been building. Now we're at a point where you can set off on your own and start to build your own neural networks or improve performance on the existing ones that we built. So how do you go about doing that? Well, I've put together a 10-point plan here for optimizing the performance of your deep neural networks. So the first step, the first thing that we need to do is obtain above chance learning. If you don't have above chance learning, so with the 10 MNIST digits, if you're not getting above 10% classification accuracy, it's going to be tough to figure out how to make any improvements in your model. So if you're performing below chance or at chance, a good first step is to simplify the problem. So for example, with the MNIST digits, you might want to strip away 8 of the categories and just work on distinguishing zeros from ones. Or with the Oxford flowers, the same kind of idea. Instead of trying to distinguish 17 different categories of flowers, you could just pick 2 and try to distinguish those. If we were working with a different kind of data set, like movie ratings, for example, and you're trying to guess the sentiment of the movie ratings, then you could simplify the problem by retaining only the most positive and the most negative reviews, the 1 and 5 star reviews, getting rid of the middle ones. So that's one idea, simplifying the problem. Another way that you could try to obtain above chance learning is by simplifying your network architecture. So maybe you've put together this really deep, elaborate, convolutional neural network and you're not getting any good results. Well, simplify things. So comment out some of your layers and start with just a simpler architecture. And another idea for obtaining above chance learning is to reduce the size of your training data. So that allows you to iterate more quickly. If it only takes a few seconds between epochs, then you'll be able to get a sense of what's working, what isn't working more quickly than if you have to wait minutes or hours per epoch. So once you've attained some above chance learning, then it's time to start thinking about how many layers you have in your network. Depending on the problem that you're trying to solve, adding more layers could help you deal with the increasing levels of abstraction that you have in your data. On the other hand, you could potentially add in too many layers, which slows down learning and which makes it more difficult for the neural network to do any kind of accurate classification. So you can vary the number of layers in your neural network both by adding and subtracting layers and seeing where you get better accuracy. In addition to varying the number of layers, you might want to consider varying the type of layers. So we've gone over a number of different kinds of layers here: dense, softmax, max pooling, flattening, and convolutional layers. They all have different attributes that we've gone over the previous lessons, and depending on the problem that you're trying to solve, using a convolutional network to extract some spatial information, using max pooling to reduce the size of your layers, the size of your data that you're processing, or using dense layers to recombine information, your choices have an impact on the results, and so you want to think carefully about which layers you're putting in and where. Finally, after we've decided on the types of layers that we're going to have and we found an optimal depth of layers, then we're going to want to start playing around with the width of the layers. So typically people use orders of exponent 2, so 64 layers, 64 neurons in a layer, 128 neurons in a layer, 256 neurons in a layer, and so on. So you can play around with varying the width of your layers and seeing how that affects your validation accuracy at the end. After we're finished with these 2 steps, you want to be sure that you're initializing everything in your network properly. So we talked about this. This is a relatively easy step because we really just want to be using a GLORA initialization. Whether you use uniform or normal typically won't make too much of a difference, but that's definitely your best pick. Another option that we've talked about a bit is your choice of cost function. So we decided, and based on the results that we were seeing in the networks we were building, that cross entropy learns a lot faster. You'll avoid learning slowdown by using cross entropy instead of a quadratic cost function. So we'd recommend sticking with the cross entropy there. To avoid overfitting, we covered a whole section on this in an earlier lesson, so you can go back to that. Just to recap, the kinds of things that we want to bear in mind are that if our network is overfitting, that could be just a function of training our network too long. So by looking, say, on your tensor board at how your validation accuracy is changing, once it plateaus, or if your validation accuracy starts to go down, you've overtrained. So if you're seeing that after 50 epochs, your validation accuracy is reaching a peak, then you can stop your training right then. Early stopping is a common approach to avoiding overfitting. And then, of course, we also have dropout as an option. So playing around with the proportion of neurons that you're dropping out in your different layers and seeing how that affects your validation accuracy. You can expand your data set, for example, by adding noise to the data or moving images around. And of course, you can regularize in your layers. You can penalize large weights with L1 or L2 regularization. After clearing these top 5, we can have a look at our learning rate. So you want to monitor the cost in your network, how quickly your cost is decreasing over epochs to tune your learning rate. For most of these hyperparameters that we're talking about here, you want to be monitoring accuracy, but with learning rate, it helps to look at your cost. Initially, you want to adjust your learning rate by orders of magnitude to find a relatively smooth cost curve. You don't want to have your cost jumping up and down. You want to have a minimal amount of oscillation in that curve. And then you can actually set a variable learning rate schedule so that at the beginning, when there's a lot of learning to be done, you have a fast learning rate, and then near the end, as you're approaching your minimum cost, you can slow down your learning rate. One option that we've talked about to avoid worrying about calibrating your learning rate in this way is to simply use a advanced gradient descent approach like Atom, which takes care of that for you. The next hyperparameter that we want to tune is the number of epochs. We touched on this briefly in the avoiding overfitting section. After you have your learning rate established, you're going to want to calibrate your number of epochs again, because the learning rate, if you change that by an order of magnitude, then theoretically you might need an order of magnitude fewer or more epochs to be training your network properly. So you'll want to be checking your number of epochs again here. After that, if you are using L1 or L2 regularization, then you have an additional parameter lambda on that regularization that you can fine tune. So you can start by changing that by orders of magnitude. So you might start with 0.01, bump that up to 0.1, drop it down to 0.001. You can fine tune after you've found a high performing lambda by the order of magnitude changes. After you've fine-tuned your lambda, you're going to want to go back again, check out your learning rate, check out your number of epochs. In step 9, you're going to want to calibrate your mini batch size. So remember that with stochastic gradient descent, we're not training on our entire data set with every step. We're deciding on a subset of our training data to work with. So the optimal mini batch size varies as a function of a number of parameters. So depending on the availability of memory on your machine, the dimensionality of your data, or the complexity of your neural network architecture, you'll have a different mini batch size. Typically, people vary their mini batch sizes by the exponent 2. So you might start off with 128, reduce to 64, increase to 256, and see how that affects your training speed as well as your training accuracy. If your mini batch size is too large, your model weights won't be updated enough. If your mini batch size is too small, then you're not making the best use of the hardware and software resources that you have available to you. After you've found an optimal batch size, then once again, we're going to want to go back and have a look at our learning rate hyperparameter, our number of epochs, and our regularization parameter lambda. Because of all of this going back and recalibrating, doing this manually can involve dozens of iterations over this process. If you think that's a bit arduous, there is a solution. So there are automated techniques for playing around with your hyperparameters. You can use what's called a grid search to explore various changes in these hyperparameters, particularly hyperparameters 6 through 9. And Joshua Bengio has done research out of the University of Montreal that recommends not using fixed points for the values in that grid search, but randomly selecting them from a distribution. That tends to get high-performing results more quickly. And finally, there is open source software available for optimizing your hyperparameter searches automatically. So for example, there's a package called Spearmint that you can use.